All right, May, tell me what you got for 3. Tell me what radiation is.
It's the transmission of radiant energy through electromagnetic waves.
Good. So it's transmission of energy or transmission of heat. Of heat through electromagnetic which I frequently will call EM waves. So it's the transmission of heat through electromagnetic waves. Mostly, that is infrared. Mostly, that's infrared. That's why if you use infrared goggles, what you see is the heat of objects. Okay? So objects that are hotter are brighter. Objects that are colder are like bluer, greener, darker kind of colors. Okay? This is the least efficient form of heat transfer. Okay? But everything does it. Mm-hmm. Everything does it. Everything does radiation. There's not a single object on the planet that does not give off radiation. Now, there's some things that give off less radiation, but everything gives off some. Okay, so how does it work? What colors have I been using? There we go. So how does it work? Higher temp objects give off more electromagnetic waves and therefore heat. This is going to be something we talk a lot about. Well, let me give the example first. Okay, so objects that are higher temperatures give off more electromagnetic waves and therefore give off more heat. Best example of this one is either the sun or fire. Both of these are good examples. Both of these are good examples. The sun is hot, and it gives off radiation, and that's what we feel here on Earth. Fire is hot. It's not a physical thing. You can't grab it. Okay? That's because fire is electromagnetic waves. It's radiation given off. Okay? So you're feeling the heat of the fire. You're feeling the radiation given off. Okay? But as I mentioned, everything does this. Everything does this. If you put your hand over your other hand, you can feel the heat between your hands. Okay? It's not going to be hot, but you can feel the warmth between them. Okay? And that's because you're radiating heat. If you go outside in the winter without a jacket on, the reason you are cold is because you are radiating heat off more than what the heat is being transferred into you. Okay? That's why you feel cold. The reason you wear a jacket is because then you radiate the heat off, but it gets stuck inside the jacket and it warms you back up. Okay? That's why emergency blankets are basically just tin foil, because you radiate the heat off your body and it reflects the heat back into you and warms you back up. That's also why in emergencies with these emergency blankets, you're told to get naked. Because if your clothes are wet, which they usually are in these kind of emergency, like winter scenarios, when you do that, you're going to radiate more body heat, which will get reflected more back to you. So there you go. Again, survival tips with Mr. B. You never knew things you needed to know in physics class. Okay. Let's see. Grady, what you got for A? Space is a vacuum. No particles exist between Earth and the sun. So how does the sun warm the Earth? Yeah, it's electromagnetic waves. So no particles are transferred just energy in the form of waves. Now, here's the really interesting thing. We'll talk about this more when we get into space and astronomy, and particularly we're going to do a whole section in astronomy on stars. Stars are fascinating. Here's one interesting thing about stars. You may or may not know this, but not all stars are the same color. So our star is orange. There are red stars, there are blue stars, there are violet stars, violet-ish. They're not purple, but they're kind of like borderlining on like blue-violet. White stars, there's lots of different colored stars. The difference in those stars is how hot they are, their temperature. Because temperature affects what type of radiation they give off. And one form of radiation is color. I talked about infrared, but color is another form of radiation. So the color of the star tells you how hot it is. So we know how hot our star is because it's orange. And orange stars are 6,000 degrees, or 6,000 Kelvin, about. Red stars are like 4,000 Kelvin. Blue stars, some of them, like a really dark, almost violet stars, can be up to 10,000 Kelvin. So based off of the temperature, we can figure out how hot it is. This is also why, if you look at flames, the bluer flames are hotter than redder flames. So frequently, near the base of a flame, it's kind of bluish or maybe even like yellow-orange. And near the edge of the flame, where it's getting away and losing radiation, that is where it's red. So the color can tell you how hot things are. This is also why, as you heat up metals, they turn red. Because now they're hot enough that they start glowing in visible light and not just infrared. And you can see them as hotter that way. So color actually matters a lot with this, which is kind of interesting. And so a lot of what we can tell about stars is based off of their color, because we know how color is affected by heat transfer and radiation. Okay, Caleb, last one. If everything is constantly radiating heat, why don't we eventually run out of heat?
I said because everything's also absorbing heat.
Yep. It also absorbs radiation too. You ever notice on cloudy days in the winter, it's colder than a sunny day in the winter at the exact same temperature? If you go outside and it's 20 degrees, but it's sunny, it's not near as cold as if it's 20 degrees and cloudy. The reason is you're getting radiation from the sun. And so while you are giving off radiation, which makes you cold, you're also gaining more radiation from the sun, which warms you up. Not quite as much as what you give off, but enough that it doesn't feel as cold. It still feels cold, but not as cold as it was before. And again, there is conduction between the air and your skin, so that's also transferring heat as well. I've also mentioned that you don't freeze in space instantly. The reason is radiation is the most inefficient form of heat transfer. So the radiation that you give off takes a while for you to lose enough heat to freeze. Somewhere in the high 45 seconds to a minute range. So you wouldn't freeze. Now, other things would happen, like your eyeballs would explode, your blood would boil, and stuff like that. But you wouldn't freeze. That doesn't sound like fun, Jen. You're not liking that idea? But you would not freeze to death instantly. You would freeze, but you'd probably die from other things first. Yeah.
How do we predict the next temperature? The next day?
Oh, like you're talking about weather? Yeah, good question. So the way that they can predict temperature, temperature has to do with a lot of things. But part of what it has to do with is pressure. They can predict how the pressure will change. And based off of the pressure, they can figure out how that impacts the weather, right? We talked about things that are more dense will be warmer and things that are less dense will be. So you talk about they talk a lot about high pressure and low pressure areas. It goes from high pressure to low pressure, so they can see how that will change the temperature. A lot of it has to do with how much moisture is in the air. So if there's a lot of moisture in the air and the air is stationary, that'll cause it to warm up more. but if it rains, afterwards it cools off because now it gets rid of some of that extra moisture, and that causes it to cool. They can also take into account how sunny it's going to be, how much radiation that would create. Meteorology and weather is really fascinating. It's really complicated, which is why they're wrong all the time. Like, they're wrong all the time because it's so complicated that, like, just from, like, minute to minute, one little change can change everything. That's why, like, they can predict, like, there's going to be a big storm, but they don't know until, like, the day of really, like, is it making tornadoes or not? Because, like, the conditions are so specific that they have to be exactly right if you want to make it. Meteorology is fascinating. I took a meteorology course in college because I found out my senior year that apparently I had to take one. And it was really interesting because the professor found out that I was a physics major early on. And so we would, like, spend the whole class talking about, like, interesting physics, weather, math stuff. And then he'd get to the end of the period and you'd be like, oh, by the way, none of this is on the test. Study this stuff instead. So he spent the whole class talking about things that were interesting to us but didn't actually matter to the class. The class average was atrociously bad. I was the only person with anything higher than a C, and I had an A, obviously. But it was terrific. I learned so much in that class, and no one else learned anything. It was great. So anyway, if you're going to take a meteorology class, be a physics major and take it your senior year, you'll learn a ton of stuff, and then you can be smarter than everyone else. That is the goal of being a physicist, by the way, is just to be smarter than everyone else. Any questions on radiation? Cool. Last one. Newton's law of cooling, and then we'll be done for the day.